Hello guys, you're welcome to my channel. Today we'll be talking about the famous sequence that only few know about it. Okay, that statement is kind of somehow a famous sequence that few people know about it. Take it like that, don't worry. Today we want to talk about the Fibonacci sequence. You are all familiar with every other type of sequence in the basic class, like the geometry sequence, linear sequence, harmonic sequence, that is AP, GP, and HP. But today we want to look at Fibonacci sequence and the golden ratio. Now, what is Fibonacci sequence? You already know that the member of a sequence is what we call the term in that sequence. Now, how do we generate the term in the sequence? Like for AP, GP, you always use what? T, N to denote what? The term you are talking about. So, for this now, we are going to be using what? Fn to denote what? The sequence in Fibonacci, where the F simplified that what? It is a Fibonacci sequence. Now, let's quickly look into how we go about that. Okay? If I have that n is equals to 0, I will have that f of 0 is what? Is 0. If n is 1, f of 1 would be 1 as well. If n is 2, f of 2 would also be what? 1. If n is 3, f of 3 is going to be 2. If n is 4, f of 4 will become what? 3. And if n is 5, f of 5 will still be 5. Then if it is 6, it's going to be what? 8. If it is 7, it will be 13. Are we together? And the next one is going to be what? 21. And the next one is going to be what? 34. And the next one will be 55. And the next one will be 89. And the next one will be 144. And the next one will be 233. And so on like that. Now you will ask me, how do we generate all this sequence? That is, all this member in this particular sequence, how do we generate them? It's very simple. Now, you know that for your AP, you have that for any sequence is going to be the first term plus n minus 1 times the common difference. And this is how you get successive member of what? Of AP. And if you're getting the successive member of GP, that will be A times what? The common ratio n to power of minus 1. So this is what you use to generate the common what? The successive term in this particular what? Sequence. Isn't it? We call this the nth term of GP, and this is the nth term of AP. What will now be the nth term of the Fibonacci sequence? I'd like you to observe something. If you look at this now, when n is what? When n is 0, the value is 0. When n is 1, it is what? 1. Now, when n is 2, how do we get the value? But the value here is what? Is 1. Because, if you start from the beginning, you're like, f of 0 is 0. F of 1 is 1. If you want to predict f of 2, you said it's 2. And f of 3 will be 3. But no. So, after getting the first two terms, when n is what? Equal to or greater than 2, for us to get that term, we had the what? The two terms that precede it. That is 0 and 1 come before what? When n is 2. 0 plus 1 will give us what? 1. If I'll get the next term, 1 plus 1 will give me what? 2. Then if I'll get the next term, 2 plus 1, that will be 3. If I'll get the next term, 2 plus 3, that will be 5. If I'll get the next term, 3 plus 5, that will be 8. If I'll get the next term, 5 plus 8, that's 13. If I'll get the next time, 18 plus 13, that's 21. If I'll get the next one, 13 plus 21 will give us 34. If I'll get the next one, 21 plus 34, 55. And that is how we continue getting it. Hence, we can say for Fibonacci sequence, f of n, that is the nth term of that sequence, is going to be f of n minus 2 plus f of n minus 1. If n is greater than or equal to what? 2. Are we together, class? Okay? If we are together, we have seen the general what? General formula for the nth term of what? Of Fibonacci sequence. Now, but there's a restriction using this. It means you have to know the first two terms that precede what? That precede the particular term you are looking for. What if you don't know those two terms also? Does that mean you cannot determine the one you are looking for? We'll talk about that as we move on in this video. Are we together? Now, you must have been hearing about a word like golden ratio. What is golden ratio? Before I talk about golden ratio, I would like to generate more of this word, of this Fibonacci sequence. Now, permit me to clean this. Now, I want to generate more of this sequence. So if I will generate the next one now, I will have that 144 plus 233. And that will give me 377. So the next term here is going to be 377. 377. And the next one, I'm going to add these two together now. And that will be 233. So that will give me 610. And I will add it to that one again. So that will give me 987. If I add these two together again, that will give me 1597. If I add these two together again, and that will give me 2584. If I add these two together again, and that will give me 4181. Let's stop here, guys. You can continue adding as much as you want, and it's fun. Okay, if that should be the case, let's go on now. What is called golden ratio? Golden ratio is the limit of the ratio of the successive term of a Fibonacci sequence. The what? The limit of the ratio of what? Successive term or consecutive term of a Fibonacci what? Sequence. Now let's look at that. If I take the ratio of this and this, that is, not let me start from here because of this 0. Let me start from here. 1 divided by 1, and that will give me 1. 2 divided by 1, that will give me 2. 3 divided by 2, that will give me 1.5. And 5 divided by 3, I will need calculator there. 5 divided by 3, that will give me 1.667. And if I pick the next one, that will be 8 divided by 5. 8 divided by 5, I will have 1.6. And the next one, that will be 13 divided by 8. 13 divided by 8, that will give me 1.625. And if I pick the next one, 21 divided by 13, 21 divided by 13, that will give me 1.615. And if I pick the next one, that is 34 divided by 21, 34 divided by 21, that will give me 1.619. And if I pick the next one, 55 divided by 34, 55 divided by 34, that will give me 1.618. And if I pick the next one, which is 89 divided by 55, and that will still give me 89 divided by 55, that will result to 1.618. And if I pick the next one, 144 divided by 89, 144 divided by 89, that will give me 1.618. And if I pick the next one, 233 divided by 144, 233 divided by 144, and that will give me 1.618. If you look at this now, you will see that as we progress, that the value of n is increasing. You will see that the ratio is tending to the same value. Right from here, you can see that is 55. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When n is 10, you can see our value is what? 1.618. When I take the ratio, when it is 11, you see it's still tending to the same thing. When it is 12, it's tending to the same thing. When it is what? When it is 1, 2, 2, 3, that should be 13. You can see, you now see that the ratio is tending towards the same value. Are you getting this now? Hence, we call this a golden ratio. So the golden ratio is given to be, 1.618. Now, you will observe that as you progress, that the value of n increasing. Are we together now? The Fibonacci sequence is approaching what? A geometric sequence. Because for them to be having common ratio right from when n is what? When n is equal to 10. You can see from when n is 10, you can see they are having what? They are having the same ratio. Hence, it's tending to become what? A geometric sequence. Because a geometric sequence is the one that have what? Common ratio. Now, for you to get, if I want to get this term here now, if I multiply the 12th term, this is when n is equals to 12. If I multiply it by this golden ratio, I will have this approximately. So, if I see 144 multiplied by 1.618, and that will give me what? 232.99. 232.99. Can you see that now? This is approximately what? 233, which is this. If I multiply 233 by this golden ratio, I should be having this next one approximately. So 233 multiplied by what? 1.618. And that will give me what? 376.994. Approximately 377. So as the value of n increase, the Fibonacci sequence is approximately what? A geometric sequence. Do we understand that now? Good. Now, that is what they call golden ratio. Now, let's take, for instance, there's possibility for me to reduce this sequence also. That is, if I want to get the term that precedes what? 144. I can also do the same thing by taking the reciprocal of this. If I take 1 all over what? 1.618, I should be having 0.618. If I multiply 144 by 0.618, that is, I'm reducing what? The sequence now. 144 multiplied by 0.618. 144 multiplied by 0.618. I'll be having what? 88.992. And this is approximately what? 89. You can see we have 89 before 144. So if I use this to multiply 89 again, I should be having this approximately. But once the value of n is reducing, it's not going to work again. And that is why we said what? When the value of n is large, the Fibonacci sequence is approximately a geometric sequence. Only when the value of n is what? Large. Do we understand that now? Now, which other beautiful things do we need to understand about the Fibonacci sequence? And what we need to understand about Fibonacci sequence now is the fact that if we have something like, if I'm giving you one of these terms, let's take for instance that I gave you the 13th term, that is when f of 13, and that is 233. And I'll say find f what? F20. For instance, you are given that f13 is what? 233. Find what? F20. How can you get this? You already know that when the value of n increase is approximately what? A geometric sequence, isn't it? Whose ratio is approximately what? The golden ratio. Are we together now? Hence, I can get the value of this by using this formula, saying that what? F of 13, f of 20 that we are looking for is equal to f of 13 multiplied by the golden ratio. Now, what number will I add to 13 that will give me what? 20. And that is what? 7. It means if I multiply this particular what? Term by what? By the golden ratio 7 times. That is, I use the golden ratio to multiply this term 7 times. I'm going to have what? The 20th term. Are we together? So, if that should be the case, we can now say this is what? 233 multiplied by 1.618 to the power of 7. So let's press our calculator and let's see if we are going to have the actual value for that. So 1.618 to the power of 7 will give us, okay, let's multiply it by 233. So we have F20 to be 676.4.0. Okay, and do we have F20 here? Do we? This is 12, 13, 14, 15, 16, 17, 18, 19. Okay, we can get our 20. Let's add these two together. Let's add that two together. So we have what? 4181. 4181 plus 2584. And that gives us 6765. That gives us 6765. So approximately, this one also is that. If we approximate, you can check your calculator. So approximately, this will give us this. Do we understand that now? Okay. So if that should be the case, we can move on to the next thing now. And what's that next thing to look at here is how to determine the value of the golden ratio. But before I look into that, there's another unique thing about what Fibonacci sequence. If I take the geometric mean of this term and this particular term here, I'm going to get the one at the middle. That is the geometric mean of this term and this term will give us this. That is F13 is the geometric mean of F12 and F14. And let's see if that will be true. So F12 is 144, then multiply by F14, that's 377. Okay, let's see that. 144 multiplied by 377. That will give us, okay, let us waste time. Let's take the square root of answer. So we have F13 to be 232.997. And this is approximately what? 233. You can see the geometric mean of what? Of the term that is preceding what? A term. And the term behind it. Are we getting it now? When we take the geometric mean of them, it's going to give us what? The middle term. You can try that with another number. And let's see. Now, how can we determine the value for the golden ratio? That is where we need to move to now. So, I'll be determining the value. I'm going to derive an equation now to determine the value of the golden ratio. Likewise, I'll talk about the general the general formula to determine any term in the geometry in the Fibonacci sequence without you knowing any of the term before. Kindly pay attention. Okay? If that should be the case, if I have that the Fibonacci sequence Fn is given as Fn minus 2 plus Fn minus 1, where n is greater than or equal to 2, like that. If that should be the case, if I divide, this particular sequence now, I can rewrite this as f to power of n equal f to power of n minus 2 plus f to power of n minus 1. Now, if I divide through by f to power of n, like this, I will have this to become what? 1 equal f to power of minus 2 plus f to power of minus 1. Remember, this is going to be, fn minus 2 divided by fn. That will be fn minus 2 minus n. This and this will cancel. That's why we have this left. And if you look at this also, that will be fn minus 1 divided by fn. And that will be fn minus 1 minus n. This and this will also cancel. That's why I'm having this left. Do we understand that? Okay? If that should be the case, then we are good to go here. So the next thing I need to do here is to divide by f to power of minus 2. And if I do that, f to power of minus 2, if I'm dividing by that, I will have what? The result of this particular sequence to be f squared to equal what? 1 plus f. Are we together? F squared equal what? 1 plus f. Okay? If that should be the case, I can rewrite this equation to be f squared minus f minus 1 equal 0. And this is what? This is a quadratic equation, isn't it? Yes. If that should be the case, remember that as n increase, the f of n is proportional to the golden ratio. Are we together? So if that should be the case, f to power of n will be proportional to what? R to power of n. So f to power of n minus 1 will also be proportional to this. And fn minus 2 would also be proportional to what? R n minus 2. And if that should be the case, I can replace what? F squared with r. So I have r squared minus r minus 1 equals 0. And the reason why I'm replacing with r is because I'm looking for the ratio so that I can get what I'm saying now. Now if I apply what? The quadratic equation to this, I'll have that my r is equals to minus b, and this is 1, so this is going to be 1 plus or minus the square root of b squared, and that's negative 1 squared, then minus 4 into a, then into c, which is this, then divided by what? 2a. And that's the quadratic formula. So r is equals to 1 plus or minus the square root of 1 plus this, and this will give us what? 4 divided by what? 2. And that is 1 plus or minus the square root of 5 divided by 2. Okay? If that should be the case, our r is either what? 1 plus the square root of 5 divided by 2, or r is equal to 1 minus the square root of 5 divided by 2. And that is our golden ratio. Okay? I think it's nice. Can I clean this? Yes. So if I clean this now, I have that my golden ratio r is 1 plus the square root of 5 divided by 2, or you say r is equals to 1 minus the square root of 5 over 2. So this is golden ratio. We use this to what? To increase, and we use this to do what? To decrease. But for you not to make a mistake, we always take the positive value of this. So we take the root of 5 minus 1 divided by 2. And this is equivalent to the 0.618. And this one is equivalent to the 1.618. If you press your calculator, you should be having these values. This is what we call golden ratio. And I think we see the way we got it. Okay? Okay, guys, let's see the general formula for Fibonacci sequence. So if you want to determine any term in Fibonacci sequence, how can you do that? That is what we want to look at now. Okay? Now, I would like to take the formula right from when f is to power of n equal when f is to power of n minus 2 plus when f is to power of okay, let me take it like this so that we're not going to be deriving the golden ratio. Okay, fn is this, which is the general formula for Fibonacci sequence for n greater than or equals to 2. Yes, we remember this. This is the general what formula to form any term in Fibonacci sequence. Now, if I now have this is the same thing as saying what? Fn equal 1 plus the square root of 5 divided by 2 to power of n plus 1 minus the square root of 5 to power of 2 divided by 2 to power of n rather. Now, this is a general formula for Fibonacci sequence now. Are we together? This is what? The general formula for Fibonacci sequence. Now let's see how we can do it so that we can use this to determine any term that we are looking for in Fibonacci sequence. Okay? We can do that. Let's consider f of 0 and f of 1. So if you look at the sequence that we generate the other time, we have our f of 0 to be 0, and we have our f of 1 to be 1. So if that should be the case, let's say this is f of 0. F of 0 is what? Is 0 equal, this will give us 1 plus the square root of 5 divided by 2 to power of 0. Then, okay, let's do something like this. Let me express this particular value like I'm expressing the result in what's it called? Linear ordinary differential equation. That is second order linear ordinary differential equation. If you look at this particular question here, it looks like what the result or the result we are going to have when we have the second degree ordinary differential equation. That is, if I have linear differential equation, we are still going to get there by His grace. If I have linear differential equation, I can express my answer in terms of some constants. Let me choose those constants to be P and Q. So if this is f of n equal what? P into what? 1 plus the square root of 5 divided by 2 to power of n plus Q to 1 minus what? Root 5 divided by 2 to power of what? N. So this is what? This is my result for ODE. Second what? Second order linear differential equation. If this is it, let's determine the value for P and Q. Now, f of n, let's say when n is 0. If n is 0, this one is also what? 0. So we have P into what? 1 plus the square root of 5 divided by 2 to power of 0. Then plus Q into 1 minus root 5 divided by 2 to power of what? 0. Anything to power of 0 will give us 1, provided that it's not what? 0. So this is going to be 0 equal what? P times 1, then plus Q times 1. So I have that P plus Q equal what? 0. So I'll call that equation 1. So if this is my equation 1, then I can get my equation 2 right from here also. So when n is 1, f of n is also 1. So if that should be the case, I have that 1 is equals to P into 1 plus root 5 divided by 2 all to power of 1, then plus Q into 1 minus root 5 divided by 2 all to power of 1. Hence, I will have that P into what? 1 plus root 5 divided by 2, then plus Q into 1 minus root 5 divided by 2 equal 1. And that will be our second equation. So let's clean this now and write down the equation so we can solve it simultaneously. Okay, so the first equation is P plus Q equals 0, equation 1. And the second equation is P into what? 1 plus root 5 over 2, then plus Q into 1 minus root 5 over 2 equal 1. And that is our second equation. Now, using elimination method, if I'm to use elimination method here, I will have that, or can I just make it simpler by saying, okay, from here, if I make P the subject of the formula, I will have that P is equals to negative Q. So if P is equal to negative Q, so I can put my negative Q into equation 2. So I have what? Negative Q into 1 plus root 5 divided by 2 plus Q itself into 1 minus root 5 divided by 2 equal what? 1. Okay, if that should be the case, then I can factorize out Q. So this is Q into what? Minus 1. Then this will be minus root 5 over 2 plus 1 minus root 5, everything over 2, because they are the same what? LCM. And this equal what? 1. So this and this will take care of themselves, and this plus this will give us negative 2, right? Okay, so Q now is going to be negative 2 root 5 divided by 2 equal what? 1. So this and this cancelled. Hence, I have that my Q is negative 1 over root 5. So if Q is negative 1 over root 5, then our P is going to be what? 1 all over root 5. Because P is equals to negative Q. So if I use negative to multiply this, I have it to be positive. And that's so simple. Then we have our results to be. So we are going to have that f of n that equal what? That equal p into 1 plus root 5 divided by 2 to power of n, then plus q into what? 1 minus root 5 divided by 2 or to power of n. So if p is this and q is this, then we have that f of n is 1 all over root 5 into 1 plus root 5 over 2 all squared, then minus 1 all over root 5 into 1 minus root 5 over 2 all to power of n. And that will be the general formula for Fibonacci sequence. So let me write it here clearly before we call it a class. So cool. So we have that our golden ratio is 1 plus the square root of 5 over 2, or we have it to be 1 square root of 5 minus 1 over 2. So we use this one to reduce, we use this one to increase. And the general formula for the nth term of the Fibonacci sequence is 1 all over root 5, then 1 plus root 5 divided by 2 all to power of n minus 1 all over root 5 minus root 5 divided by 2 all to power of what? N. So this is the nth term of Fibonacci sequence. So you can use this to determine any term in Fibonacci sequence. So let's say for instance that I want to find what? The value of my F12. Let's see if this can give me. So this is going to be 1 all over root 5 into 1 plus root 5 divided by 2 raised to power of 12, then minus 1 over root 5 into 1 minus root 5 divided by 2 all to power of 12. Okay, this is not 55, so this is square root of 5. Okay, so 1 plus root 5 divided by 2, then raised to power of 12. Okay, if I divide it by root 5, okay, I have F12 to be 144.00 minus this will give us 1 minus the square root of 5 divided by 2, then raised to power of 12, okay, divided by root 5. Okay, so we have this to be 0.001388. So if I subtract this from this, it's changed nothing. So F12 is 144. So you can see like that. And that is going to be the end of today's class. Thank you for watching. We'll meet in the next class by His grace. Have a nice day.